Okay, so we have the factors affecting acid strength. And we already went through that. So we're going to start with the first one in detail, the element effect. So the element effect, we're talking about the element to which the acidic hydrogen is directly attached. So here we could be talking about a hydrogen that is attached to an oxygen, right, in the case of water. Or we could be talking about a hydrogen attached to a sulfur. So when we're looking at H2O and we're looking at HS, we think about comparing sulfur and oxygen. So what do? Well, you go back to your periodic table and you look at the atoms that you want to compare. So remember, I used the example of H2O and HS. Well, here's oxygen and here's sulfur. So they're in the same column. And remember that as you go down a column in the periodic table, you are increasing in size, which would mean that sulfur is larger than oxygen. So it just so happens that the hydrogen on the sulfur is way more acidic. So when we're talking about Bronsted acids, Bronsted-Lowry, if you're comparing down the column, then you're going to be looking at atomic size. So if you see the atomic numbers are increasing, so the general kind of rule here is that as the atomic number increases, the acidity also increases. We could also be comparing across a row. We could be comparing a hydrogen attached to a nitrogen or a hydrogen attached to a fluorine, for example. When you're comparing left to right, also see that the atomic number is increasing. And the reasons behind this, you're going to be looking more at electronegativity than size of the atom. And we'll talk a little bit more about that later. But so far, we've said that down a column, acidity is increasing. And that has to do with size. And across a row, from left to right, is increasing, and that has to do more with electronegativity. So we see that here on this slide. Acidity increases as you go from left to right on the periodic table and from top to bottom. We're going to talk about the element effect in terms of the ionization process briefly into these 3 steps here. So there's bond breaking, which has to do with the bond dissociation energy, which has to do with the bond strength. So that's going to be talking about the bond between the chlorine and the hydrogen in the example of HCl. How strong is that bond? How much energy is it going to give off when it's broken? We can also talk about the ionization potential. And we can also talk about the gain of the electrons by the conjugate base. And you can connect that with electronegativity. So looking at bond breaking, the important thing here is to know that the easier a proton comes off, then that will make it a stronger acid. A stronger acid is an acid that is going to dissociate more completely. So the less energy that bond gives off, the less strength that bond has, the better the acid and the stronger the acid. So when hydrogen loses an electron, remember that like for example, when it's sharing a bond with chlorine, and when it loses that bond, it becomes H+. So the ionization potential is how well it can carry that positive charge. How good is it at ionizing? And so since every Bronsted acid has a hydrogen, and we're talking about hydrogens, then that's relatively the same for acids, all acids. Next, we talk about the gain of an electron by the conjugate base. So here we're talking about when an acid loses its proton, it gains electrons, and it becomes its conjugate base. And the more stable it is after it's gained those electrons, and it is a conjugate base, will also affect how acidic how acidic the conjugate acid is. If something is more acidic, it will have a more stable conjugate base. And stability is being able to carry that more negative charge. And the more electronegative an element is, the easier it is to carry that more negative charge. So, for example, if we're comparing a hydrogen attached to a carbon versus a hydrogen attached to a fluorine, what happens when that hydrogen leaves the carbon? Well, that will give a more negative charge to the carbon. Same thing over here, when the hydrogen leaves the fluorine, it will give a more negative charge to the fluorine. Fluorine is the more electronegative element, so it will be more stable than will the carbon be when it has that negative charge on it. So then you would expect the acidity to follow that trend. So the acidity of the HF would be way higher than the acidity of the H on the C. And you can kind of simplify it a little bit and just think about who is more comfortable losing that proton. Fluorine is more comfortable losing the proton because it's more electronegative and it's more comfortable with a negative charge. So let's think about bromine and iodine. Well, we just learned that as you go down the periodic table, the atomic size is increasing, and also so does acidity. Well, as size increases, so does the bond strength decreases. So the bond between the hydrogen and the bromine is going to be just a bit stronger than the bond between the hydrogen and the iodine. So that would mean that that's another reason why the hydrogen attached to the iodine is going to be easier to abstract than is the hydrogen attached to the bromine. So that would make then iodine its element effect, making its acid more acidic. So that longer bond length is going to be the weaker bond, and that's going to make that acid stronger. But then we also let's compare then nitrogen and oxygen. So when you're looking across, bond strengths aren't changing as much as electronegativity is. Likewise, when you're looking down a column, bond strength is changing more than electronegativity. So when you're looking at left to right, think more about electronegativity. So moving left to right, fluorine is going to be the more acidic species than the acid with the nitrogen in it. So general recap, if you're looking at your periodic table and you're comparing two acids and you're asking yourself which one is more acidic, you're using the element effect and you're comparing either left to right or up to down. And so think about what trends you need to think about. Are you thinking about electronegativity, or are you thinking about bond strength? And just generally, acidity increases left to right and from top to bottom. So now let's just quickly compare these. So you'll notice that we're looking at the element effect because all of these hydrogens are directly attached to one atom. So we're comparing carbon, oxygen, nitrogen, and fluorine. Well, let's go back to the periodic table. So we're comparing carbon, nitrogen, oxygen, and fluorine. Well, that's helpful because they're all in the same row. And remember, moving left to right, acidity increases. And that's because of electronegativity. So you would expect that carbon, or the hydrogen attached to the carbon, is much less acidic than the hydrogen attached to the fluorine. So let's see if that is the answer. And yes, it is. That is the answer that we get. Remember from Gen Chem, the Ka value, and Ka is the dissociation constant of the acid. And the bigger the Ka, the more acidic the species is. And we see that here. So we would expect this species to be the highest and this to be the lowest. So we have, in ranking from strongest to weakest, we have HF, and then H2O, NH3, and then CH4. So now let's try this one. And again, make sure you're trying on your own before we get to the answer. But note we are comparing iodine, bromine, chlorine, and fluorine. So here we are, fluorine, chlorine, bromine, and iodine. Well, what are we comparing here? Remember that we're going to be looking at atomic size and the correlating bond strength. From top to bottom, we have the smaller to larger atoms, meaning we have these stronger to weaker bonds. So we would expect the weaker bond strengths to be the stronger acid, so that would make iodine the stronger one, and fluorine up here the weakest. So let's check that with pKa's. And yes, indeed, that is what we have. And remember that Ka also, it's also associated with the pKa, and so remember the difference between those two, and we'll talk about that a little bit later, but we use pKa more than Ka in organic chemistry.